Let's see what this looks like in an algorithm. Instead of starting with one node at 0 and working our way out, we start with these estimates at every node. So originally, because U is connected to V, W, and X here, we know some initial estimates going from U to V, W, and X. We know that it costs nothing to get to itself, but we don't know for Y and Z because they're not neighbors of U and they're not U itself. Bellman-Ford now works like this. We pick one of these nodes. I'm going to pick U again. And that's our purple node. We consider all of its neighbors. But now instead of pushing information out to the neighbors, we ask each neighbor for its table. So we've picked V and we've gotten V's table. We know that V is 2 away, and so we add this number to this number and compare it to each of our cases. If we go 2 away to V and then back 2 to get to U, that's not better than just staying at U, so we leave our current estimate alone. And the same for V, and the same for W. We could go 2 away to V and then 3 on to W. That's not better than our current. Also, going to X is no better. And in the case of Y, 2 plus infinity, we treat as infinity. That's not any better. It doesn't look like we're making any progress here. But that was taking information from V. Let's consider information from W instead. If we look at W's table, we still can't do any better to get to U. We still can't do any better to get to V. Can't do any better to get to W, and we still can't do any better to get to X. But to get to Y, we now know that we can get there in 5 steps to W and 1 more step to Y. So we refine our estimate to 6 for Y and check Z, and we find also that we can get to Z in 10 steps. So at this point, we have a revised estimate for U. As we move on to the next neighbor X and use its table, we find we cannot improve our answer for U. We cannot improve our answer for V, but now we have a better way to get to W, because 1 plus 3 is better than 5, so we change that. No better for X, but Y we now have a better route, and Z we do not have a better route. So after considering X, then U has this estimate. At this point we've considered all the neighbors of U, so we will pick another node V and do the same thing, considering its neighbors, and I'm only showing the comparisons here that succeed and refine the estimates. We move on to X, consider all of X's neighbors, move on to Y and consider all of Y's neighbors, then Z, considering all of its neighbors. Once we've tried every node and considered each of its neighbors and merged the tables, we've got now routing tables for all of our nodes, but these may not be the best routing tables. Since the tables that we end up with after visiting all the nodes are different than what we started with, then we'll try the whole thing again. So in iteration 2, we start again with U, consider its neighbors. Consider V's neighbors. Consider W's neighbors. Z's neighbors. We also considered X and Y, and they didn't have any better tables. So we've got refined estimates in many of the tables, but how do we know that we're done? We just try again and see if we can do any better. It turns out on iteration 3, nothing happens, and so that means we found the fixed point and we found the optimal routings. Similar to Dijkstra's algorithm, we can do one iteration of Bellman-Ford locally, concurrently in each node with respect to the other nodes. We do need to get information from other nodes, but the only information we need at a node is a table from an adjacent node. We don't need global knowledge or global communication. In addition, this algorithm can be more asynchronous because if in that pairwise communication a slightly out-of-date table is sent because it's being updated to something better, we will get that updated table later and still eventually converge to the right answer. So it can be more distributed, this algorithm, and we'll see that that leads to its application in different routing problems than Dijkstra's algorithm.